For simpler or comparator noise evaluation, we introduce a Trannoise analysis, which should be precise enough. However, we may need other more elegant methods like a periodic steady state PSS, periodic noise Pnoise analysis, or even a hand calculation. Before showing other elegant methodologies, why don't we like the Trannoise analysis? Correct. Simulation time. If you are familiar with a time domain simulation, you will notice that the clock time step could be too small at a high speed, and the stop time may need at least 10,000 cycles for just one input swing. If we need to target the input noise within 2 mV IMS range with a 0.1 mV voltage step resolution, you may need 200,000 clock cycles simulation over all PVT conditions, which would be very time consuming. In addition to the simulation time issues of the sample's noise verification, what else could be the issue? Think about the design images for 5 seconds. Bingo! The Trannoise simulation is a brute force way of getting the IMS noise value, providing no design insight. For example, do you know what the noise contributor from the Trannoise result? If not, how do you know which device damages the noise and then to reduce it effectively? So obviously, the Trannoise would only provide the circuit verification for tap-out sign-off, but not the circuit design information for you. Alright, after understanding the time and design limitations of the Trannoise, what kind of other method can you try? Think about the periodic image for 5 seconds. Right, the most time consuming is the transient simulation is the sampling clock, which has periodic properties. Then we don't really need to run the whole time domain transient simulation for the sampling circuit, including the clock. Instead, we could just run a few cycles of the transient simulation and determine the steady state response of the simulated circuit at a special bit frequency, which is called periodic steady state PSS analysis. After reducing the simulation time to get a steady state operating point, what's the next step? Correct. Similarly, the next step is the periodic noise Pnoise analysis. After the PSS analysis, the sample's periodic operating point as a starting point for the periodic time-varying Pnoise analysis. The Pnoise should calculate the effect of the periodic time-varying bias point on any device that generates noise among frequencies. Therefore, as the AC noise, the Pnoise should provide a noise breakdown in different frequencies to help us understand. But in order to convert the noise from the frequency domain to the time domain, you must integrate your interest frequencies to get the IMS noise value in time. Let's go through a simple test bench of the sample's PSS plus Pnoise analysis. First, starting with the PSS simulation by setting the sample's differential input swing equals 1 mV. In addition to defining the fundamental or bit frequency of the clock, 28 GHz here, you must specify the number of harmonics fitted in our example, then the output net in voltage must be specified properly, which is the sample differential output in this example. After the PS analysis is done, you should see the periodic output voltage is Vp out or 20 mV in this example. So you can define the sample's periodic gain as 20 for now, which should be a similar gain value for the noise. To start the Pnoise analysis, you must set the number of harmonics fitted in our example as well, which should be less or equal to your PSS setting. Also, you need to specify the delay time of the starting to do the analysis, and the rule of thumb is around 100 clock cycles to help the analysis converge. Lastly, you must set the integrated frequency of the interest noise in the time domain, which is 1 kHz to 14 GHz next rate in this case. As the AC noise analysis, we should get the total output integrated noise, which is 17.55 mV IMS here. Then we must divide by the gain to get the input referred noise, 0.88 mV IMS. The PS or the Pnoise setting might be slightly different in each tool, and please refer to the menu of your tool. Here is just my personal experience of running the PS plus Pnoise of the sampler in the past. The most encouraging thing is that the 0.88 mV IMS of the PS plus Pnoise is close to the 0.9 mV IMS of our previous Trannoise. Therefore, both could be a sanity check against each other. What else do you expect? Right, the beauty of the PS plus Pnoise not only speeds up the simulation time, but also provides a noise breakdown such that we can identify the dominant source from the noise contributor pieces. Circuit designers can optimize their block easily to reduce the noise effectively without binding resizing. For the sampler's case study, you will notice the main noise contribution are from the sampler's input differential pair. Then, how should you make the design better to reduce the noise? Correct. Then you should go back to the fundamental noise model from the literature or textbook. From the reference, we know all the parameters here from the operating point of the sampler. Then it's easy to do a quick hand calculation without any surprise shown here. The calculated input referred noise is 0.82 mV from the input differential pairs, which is slightly lower than the values of the PS plus Pnoise or Trannoise. So you can trust the modeling here to reduce the noise either by reducing the overdrive of the differential pair or increasing the threshold voltage of the cross-coupled NMOS pairs. The most effective way was probably to increase the capacitance at the drain of the differential pair, but to trade off the sampler's speed. Here are the summarized images of why we need a periodic steady-state PSS, periodic noise, Pnoise analysis, or even a hand calculation in addition to the Trannoise analysis we introduced. The Trannoise analysis is a brute force analysis, so it's not only time consuming, but also provides no other design insight like the noise breakdown. Therefore, the Trannoise is only for tape-out sign-off verification, but not a design tool during the design phase. On the other hand, the PSS plus Pnoise not only reduce the simulation time, but also provide the noise contributors list, such that any designer knows where to optimize the noise reduction effectively. Once identifying the main noise source, the designer can also apply a quick hand calculation before running the simulation intuitively without binary sizing. So both the PSS plus Pnoise and hand calculation from a simple modeling would be beneficial in the design phase. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.